Hello YouTube, thank you for stopping by. As always, please click like if you happen to enjoy this video, please click on subscribe, and if you would like to be notified when I publish future videos, just click on that bell-shaped notify button. Additionally, I'd love to hear from you, so be sure to leave me a comment and please share this video with anyone you think might also enjoy it. Alrighty then. In this video, I'm resurrecting an educational slideshow that I narrated back in June of 1997 for the Computer Museum of America in San Diego, California. IBM had given Jim and Marie Petroff, the founders of the museum, the original script and slides from their 1973 IBM Speakers Bureau slideshow to use in the museum. In 1997, I was asked to do something with them, and I digitized everything. So now, for this video, I've cleaned up the audio I recorded back then, and I've refreshed a few slides to make the whole thing more presentable. Okay, let's get started.
The Computer Museum of America is proud to present The Evolution of Computers from the 1600s through the 1960s. How many? How far? How long? How much? The need for calculating dates back to the beginning of man. Although calculating advanced from counting one's own fingers to the shepherd who counted a leather pouch of small rocks, one for each sheep in his herd, to ancient accountants who kept track of figures using strings of beads and knots, we will start in the year 1600, the age of vision, the heyday of scientific revolution, when important mathematical techniques were being developed. There was very little in the way of mechanical aids to calculation. Astrolabes, clocks, sextants, quadrants were highly advanced aids to science, but they couldn't add. Although they did have special tables for calculating and special coins for counting, even the Peruvians had devised a handy gadget consisting of strings and knots called a quipu to assist them with counting. They used a form of decimal notation, and the position and form of the knot indicated tens, hundreds, etc. Still, the most widely used device at the time was the abacus, developed by the ancient Chinese and used all over the world. Abacus operators became extremely proficient, probably because they had to use mental abilities that are not needed with today's accounting machines. This fact was displayed in Japan in 1946 when an American GI with an electric adding machine and a Japanese accountant with an abacus had a competition. The abacus was faster in all except multiplication. Mathematicians and scientists had to spend hours poring over rows and rows of figures when they could have spent their time in worthier pursuits, and the poor banking clerks probably suffered the most. The first attempt to reduce the amount of time and effort spent on calculating was made by this man, John Napier, a Scottish mathematician. Napier developed a set of ivory rods with multiplication tables carved into them. They soon became known as Napier's bones. In the year 1617, he published a book named Rhabdologia, where he described the rods and their method of use. Each rod bears a multiplication table for a particular digit. Multiplication and division are handled by repeated addition and subtraction. The rods were crude, but they did work, and were used by several inventors in later machines. Napier, who is remembered for inventing logarithms, also introduced the use of the decimal point. Then, in a letter dated September 1623, Wilhelm Schickard, a professor at the University of Tübingen, wrote, "The same thing which you have done by hand calculation, I have just recently tried to do in a mechanical way. I have constructed a machine which automatically reckons together the given numbers in a moment, adding, subtracting, multiplying, and dividing." The next letter contained sketches of the machine, and a third told the sad story of the machine being destroyed by fire. No records exist of the events that led Schickard to build a calculator, although he was familiar with Napier's logarithms and the use of his rods. It's hard to tell how successful his machine would have been because he didn't rebuild it. He would have had to have overcome the problems that beset the inventors of the period, such as lack of precision work and over-rotation of wheels and gears. Schickard's concept was brilliant. He used a set of revolving, cylindrical Napier's rods for multiplication. Addition was performed by turning the dials on the lower part of the machine. These dials were connected with internal wheels with teeth on their circumference, which caused a carry as the wheel passed from 9 to 0. Subtraction was performed by reversing the wheel. This model was built by IBM Germany based on the few available drawings. It would be another 25 years before the first digital calculating machine even materialized. The next major step was taken in 1642 by the French mathematician Blaise Pascal, who was unaware of Jacquard's efforts. Blaise Pascal's parents soon realized their son was a prodigy, and his father devoted himself entirely to his son's education. However, young Pascal had been kept ignorant of geometry, so he simply invented his own. At the age of 12, he was discovered doing his version of Euclid's 32nd proposition on the kitchen floor. When Blaise Pascal was 16, his father was appointed as tax collector in their village. Blaise was his aide. This appears to be where Blaise Pascal got the idea of building a machine to handle calculations. Pascal's machines consisted of several wheels with the numbers 0 through 9 on each, closely resembling a telephone dial. A carry was performed by a weighted ratchet which gradually stored energy as it approached the number 9. When it passed from 9 to 0, the ratchet was released and in falling transferred a unit to the wheel of the next higher order. Since the wheels could only go clockwise, there was a second set of numbers on the wheels going in the opposite direction, and subtraction was done by complement arithmetic. Before Pascal perfected his machines, he tried many different methods, and some 50 models were discarded. He truly believed that his machines would save men hours of labor. However, they did not work very well. Accurate gear cutting had not yet been perfected. The mechanisms were forever out of order, and only Pascal and one of his workmen could fix them. Pascal's machines were also very expensive. Though they could do the work of half a dozen men inaccurately, the half-dozen men with their human failings were still cheaper than the machine. Technology had to wait for economics to catch up. The machines simply became conversation pieces and pretty toys. 10 are known to exist today. The most important contribution made by Pascal is that by building his machine, he proved that it could be done. Several attempts were made to develop machines after Pascal. 3 of these were developed by Sir Samuel Morland, Master of Mechanics to King Charles II of England. Again, they were quite pretty, but didn't advance any new principles and were no more successful than Pascal's machines. The next really significant step was made around 1674 by Leibniz in Germany. Leibniz, a mathematician, physicist, philosopher, theologian, historian, and inventor, had a dream: to develop a generalized symbolic language and an algebra to go with it, so that the truth of any proposition in any field of human inquiry could be determined by simple calculation. This quest was unsuccessful, but he did invent the calculus and devised and promoted much of modern mathematical notation. On the subject of calculation, Leibniz wrote, "It is unworthy of excellent men to lose hours like slaves in the labor of calculation which could safely be regulated to anyone else if reliable machines were used." Familiar with the machines of Pascal and Morland, Leibniz envisioned a calculator that could perform addition, subtraction, multiplication, and division with speed and above all accuracy. He could see their value in business and government, but his primary interest was in creating an aid to science. His machines had 2 basic elements: a collection of pinwheels for adding, similar to Pascal's, and a movable carriage that could follow decimal places when multiplying. The 2 sections were linked by stepped cylinders containing ridge-like teeth of different lengths corresponding to the digits 1 through 9. Turning the crank that connected the cylinders engaged the smaller gears above the cylinders, and these in turn engaged the adding section. Much to Leibniz's disappointment, his machines did not meet with his intended excellence. In fact, they were cumbersome to operate and inaccurate. But his invention was a critical step forward in calculator development. Theoretically, his machine could handle the 4 arithmetic functions, had a delayed carrying device, and contained the stepped drum principle which 150 years later would still be in use in the first commercially successful calculator. As far as we know, Leibniz built only 2 machines. He spent years of his life improving them so they would be practical, but the technology of fine instrument making could not yet reach the precision that was essential. Leibniz's dream was unfulfilled. The story of 18th century calculating devices is one of experiment, in which all possible changes were made to the inventions of Pascal, Morland, and Leibniz. Jakob Leopold, in 1727, proposed a circular Leibniz-type machine. Its principle was to disengage the gear wheel when the required number of teeth had meshed with the counter. The next improvements were made by the Earl of Stanhope in England in the year 1775, and again in 1777. Neither Stanhope machine embodied new mechanical systems, but they were ruggedly constructed and much more reliable. Technical skills now had a chance to catch up with inventive capacity. Stanhope also devised and published a simple demonstrator that mechanized logical relations. This was the beginning of a new attitude in which computers were to be considered as the mechanical embodiments of generalized mathematical processes rather than simple arithmetic machines. It wasn't until the year 1820 before the machine that would change the course of calculating would come to view. While serving his term in the French army, Charles Xavier Thomas de Colmar had the idea of building a calculating machine. His prototype was introduced in 1820, and 25 years later, an extremely lucrative calculator business was underway. Although Thomas used the step-drum principle of Leibniz, he also benefited from 150 years of growing industrialism, eliminating problems that had made the early machines so difficult to perfect. The step drum in the Thomas arithmometer was used in conjunction with a simple system of counting gears and an automatic carry. The success of the machine was due to the many springs and other contrivances that destroyed the momentum of moving parts so they would not carry beyond their intended point, a frequent failing in earlier machines. The machine could be set for addition and multiplication, or by moving a lever to subtraction and division. It was simple to use and accurate. Despite the enhancements in design, it met with the usual resistance to change. Scientific American wrote in 1849, Monsieur Colmar, a French gentleman who invented a calculating machine about 20 years ago, has improved it in such a wonderful manner that it is said to be one of the most astonishing pieces of mechanism that has ever been invented. But to our view, its complexity shows its defectibility, which goes to show how wrong predictions can be since the Thomas arithmometer was still selling in the 20th century. The Thomas machines constitute a branching point in the evolution of calculating machines. Until this time, commercial and scientific success had been twin goals. Design and construction rested in the hands of scientists, mathematicians, and mechanics. The Industrial Revolution somewhat changed the picture. Professional machinists were developing their skills and techniques of mass production. One path followed the perfection of inexpensive, reliable machines for commercial use, while on the other path scientists dreamt of a machine that would reach further into the complexity of mathematical thought. Which brings us to the work of Charles Babbage. Babbage was a remarkable man who had the misfortune to invent what should have been an electronic computer in the age of mechanical gears. He spent his life and his fortune in trying to overcome this obstacle. It took 100 years for the full significance of his work to be appreciated. By the time Babbage entered Trinity College at Cambridge, he was already a passionate mathematician. He and his friends formed the Analytical Society. One function of the society was to encourage English mathematicians to replace Newtonian mathematical notation with that of Leibniz, as used on the continent. Babbage's introduction to his future obsession was casual. He and John Herschel were checking some math tables and found several errors. At one point, Babbage said, "I wish to God these calculations had been executed by steam." Herschel replied, "It is quite possible." The idea lodged in Babbage's brain. In 1821, he began his 50-year struggle. Unfortunately for Babbage, his vision was too grand. No mere desk calculator, his engine would compute lengthy math tables by obtaining successive orders of difference through subtraction, and set them up directly in type so the tables could be printed without error. His first model, made with gears in shafts that were turned by a crank, could produce a table of squares up to 5 places. He contacted the British government in 1822, pointing out the advantages of his difference engine and offering to construct one for government use. At a time when government grants for science were practically unknown, he received a vague verbal agreement to underwrite the endeavor with government funds. The proposed engine was to be much grander, with 20-place capacity and up to 6th-order differences. As a number appeared in the answer column, it was to be transmitted through a set of levers and cams to a collection of steel puncheons that would stamp the number on a copper plate. Mechanically, this was an enormous order when you consider that standardized parts were still practically non-existent. Unfortunately, Babbage was his own worst enemy. Though plagued by many misfortunes, he could not learn when to stop making improvements and freeze the design. He had expected to complete the engine in 3 years, but at the end of 4 years, he had not reached his goal. Due to ill health, he abandoned the project for a year. When he returned, he acquired further funds from the government. But Babbage and his engineer, Joseph Clements, had a misunderstanding. Clements dissolved the workshop, dismissed his men, and departed with the tools and drawings. They later were returned. It was at this point, in 1834, that Babbage had an idea for a completely different machine, one that would operate more rapidly and have far more extensive powers than the difference engine. He asked the government whether he should continue with the difference engine or proceed with the new machine. It was 8 years before the government advised him that regretfully they must abandon the project. They had spent £17,000 with nothing to show, even though Babbage had spent a comparable amount of his own money. Unable to wait for the government decision, Babbage started work on the analytical engine, as the new engine was later named. He did not expect to build this machine, nor did he expect government support. But he did believe that a machine with its capabilities would become a reality at a later date, perhaps based on his completed drawings. It was to be capable of carrying out any mathematical operation. Instructions would tell it what operation to perform and in what order. It would have a memory with a capacity of 1,000 50-digit numbers. It would draw on auxiliary functions such as logarithm tables, of which it would possess its own library, and subroutines. It would compare numbers and act upon its judgments, thus proceeding along lines not uniquely specified in advance by the instructions. Certainly all of these abilities sound familiar to you, since they have come to pass in modern computers. But Babbage was attempting to carry them out mechanically, with no help from electrical circuits or electronic tubes. The design continued with plans to use punch cards to control the engine, an idea Babbage had learned from Joseph Jacquard, who had used punched cards to control his automatic loom early in the century. One set of cards would program the mill, his central processing unit, telling it which operation to perform. Another set would store the numbers to be acted upon. The introduction of punched cards crystallized Babbage's feeling that he had invented something really new, something more than just a sophisticated calculating machine. He wrote in his notebook on July 10, 1836, "This day I had for the first time a general but very distinct conception of the possibility of making an engine work out of algebraic development." Babbage had on paper completed the invention of what is today the general-purpose digital computer. Few people understood Babbage's work or realized its significance. One remarkable exception was the Countess Ada Augusta Lovelace, daughter of Lord Byron. A mathematician in her own right, she worked closely with Babbage, planned his computational problems, and has been called the world's first programmer. She also translated an article on the analytical engine written in Italian by L.F. Menabra, adding her own lengthy notes on the machine and its potential. This is the most important written work on the subject. As with the difference engine, Babbage never completed his analytical engine either, and it seems that some of his pain and frustration is showing in this picture. The assembled pieces of this incomplete machine, along with the unfinished portion of the difference engine, are at the Science Museum in London. Most of Babbage's contemporaries thought he was an eccentric dreamer obsessed with a slightly mad vision. Even those who tried to understand conceded that his engine was an interesting theoretical possibility. However, looking back from this age of the computer, Babbage looks quite different. He is seen as an unheralded prophet of the modern era, an impractical genius who could not reconcile the grandeur of his vision with the technological capabilities of his own age, and who therefore wasted most of his talents through no fault of his own. Babbage's difference engine did contribute to one highly successful venture. It inspired a Swedish printer, George Schutz, to produce his own engine to calculate differences and print tables. He and his son Edward accomplished this in 1843. They built two machines. One went to the Dudley Observatory at Albany, New York, the other to the Register General at Somerset House in England. These two machines are now in the Smithsonian in New York and the Science Museum in London. Returning for a moment to the branch in the road that led to commercial calculators, one of the beginnings of commercial calculators coincides with the typewriter and derives its concept from keyboard musical instruments. Considerable ingenuity was required to make this principle, the key-driven machine, work effectively. The first known patent was by the American Parmalee in the year 1850. The Hill machine, produced a few years after Parmalee's, as well as others that followed, had the same problem: how to prevent the machine from overshooting its mark. It wasn't until Thanksgiving Day in 1884 that Dorr E. Felt finally thought of the answer. He went shopping for the components he would need to start the project. He bought some meat skewers, staples, elastic bands and string, and a macaroni box for the casing. He didn't finish the device until New Year's Day, 1885, but the finished product was the prototype of the comptometer, the first successful key-driven calculator. Felt had solved the over-rotation problem by providing positive stops that were activated by the keys themselves. He knew his machines must calculate faster than accountants, many of whom could mentally add 4 columns of figures at one time in seconds. By 1887, he had built 8 machines and decided to try to sell them. He encountered several problems. It seemed to be as much of a struggle to get the machines on the market as it was to invent them. Also, he would have to train the operators. Such training, incidentally, turned into a highly profitable sideline business in later years. According to Felt, college professors, as a rule, ignored this step forward into mechanical mathematics, and bookkeepers seemed to think that it was an interference with their chosen vocation. However, in a few years, the comptometer, advertised as the machine gun of the office, and the Burroughs key-driven adding and listing machines became the most popular accounting machines. William Burroughs got his idea of building a calculator while working with Frank Stephen Baldwin, another inventor. He received his first patent in 1888 and had manufactured 50 machines by the next year. However, they proved impossible for anyone but Burroughs to operate. The machines were recalled, and soon afterwards Burroughs invented a corrective automatic device. Shortly thereafter, he went to the room where the malfunctioning 50 units were stored, carried them one by one to the window, and hurled them to the pavement below. While key-driven machines were making the scene, another group of machines was under development using another principle, that of the cylinder with variable number of teeth. In 1873, Baldwin applied for a patent for a machine which at all times had the capacity to add, subtract, multiply, and divide with no resetting of the mechanism and with no form of conversion for any of the processes. While employed by a lumber company, Baldwin had once been asked to repair a Thomas machine, which is probably when he got the idea to build a machine of his own. He replaced the Leibniz and Thomas cylinders with a single cylinder from whose periphery a variable number of teeth, 1 through 9, protrude according to the motion of the setting lever. The levers project through slots at the front of the machine. When the lever is set, corresponding numbers of teeth project from the wheel. With a crank of the handle, the projecting teeth gear with a cog wheel, which activates a digit wheel, and the numbers corresponding to the projecting teeth appear in the register. Baldwin joined forces with Monroe in 1912 and formed the Monroe Calculator Company. A pioneer in electric adding machines since 1922, the firm is still in business. A year later, in the Soviet Union, a Swedish man by the name of Vilgot Odhner patented a machine that was almost identical to Baldwin's, another one of those historical accidents. Odhner was working for Ludwig Nobel in St. Petersburg, and while there, with Nobel's support, began work on his calculator. His plan, to design and manufacture an industrial calculator that would be small and simple, easy to operate, and so inexpensive that practically anyone who needed a mechanical aid would be able to acquire one. In 1880, Odhner parted company with Nobel, set up his own company, and in 1886 began to manufacture the original Odhner in the Soviet Union. The machine sold well all over Europe. However, patent rights for Germany had been bought by another firm, Grimm Natalis, which improved the patents and placed a similar machine on the market. Known as the Brunsviga, it was probably more successful than the Odhner. Odhner died in 1905, but his son continued the business at the Soviet Union plant until the revolution, when he fled to Sweden. A new company was formed there in 1920 and still operates today under the name of Facet. These very light, practical, hand-crank machines were exceedingly popular. The last major developments in commercial calculating machines came from America and France. A machine that would perform multiplication simply had not yet been built. In 1878, Ramon Verrera, a Spaniard living in New York, invented the first direct multiplying machine. By direct, I refer to one turn of the crank for each figure in the multiplier, rather than the previously used repeated additions. Verrera asserted that he did not make the machine to sell the patent or to put it to use, but simply to show that it could be done and that a Spaniard could invent as well as an American. The machine, however, did not receive much publicity. In 1889, Léon Bolet of Le Mans was unaware of Verrera's patent. He built his own machine, which he named a calculeur. The machine was a direct multiplier using the principle of a built-in multiplication table. Bolet's machine was huge, handsome, and extremely impractical. Bolet built several of these machines, as well as other smaller types, but in later years became more interested in designing, building, and racing light automobiles. He founded the auto racetrack at Le Mans and helped the Wright brothers build airplanes in his factory. 4 years after Boly's invention, a machine was introduced to the market by a Swiss man, Otto Steiger. His machine made use of the multiplication table block in a commercially viable form. The machine, called the Millionaire, was developed primarily for big businesses, but it was immediately used by the scientific community as well. An astronomer by the name of Percival Lowell used a Millionaire to create tables for his calculations in search of Planet X, or as it was later called, Pluto. There was one more significant development in the business of business machines before the end of the century. The year was 1888. The event, the forthcoming United States Census of 1890. The problem was this: the results of the previous census had still not yet been tabulated, and the population was ever expanding. As early as 1884, Herman Hollerith, an engineer from Columbia University, had been toying with machines, both electrical and pneumatic, that could compile statistical information. He entered his machines in a competition held by the Census Bureau in 1889 to determine which of all available methods would be best for the next census. The Hollerith electrical tabulating system was the overwhelming winner. His system consisted of a pantograph punch for punching cards, a tabulator used to collect information from the punched cards, a sorter used to sort the cards, and millions of manila cards. All information pertaining to an individual person was punched into a single card. The card was then placed in the sensing mechanism of the tabulator machine, which had one pin for each possible position on the card. Where there was a hole in the card, the pin would pass through, connect with a bed of mercury beneath the sensor, and effect an electrical contact. This electrical contact would cause one of 40 counters on the tabulator to advance by one position. The tabulator could be wired so that different information could be counted on each pass of the card through the machine. The sorter box was hooked up electrically to the tabulator. At the same time a sensor advanced a counter on the tabulator, an appropriate box on the sorter would be activated and the lid would pop open. The operator would then place the card in the appropriate box and proceed to the next card. Although slow by today's standards, this was exactly what was needed at that time to make order out of the uncontrolled mass of data. For all of Hollerith's success and all the praise heaped on the Census Bureau, the newspapers complained bitterly when the population was less than expected in the state of New York and the state lost 2 representatives. Following the United States Census, both Austria and Canada used Hollerith machines for their own censuses. In 1895, Hollerith went to Moscow to sell his machines to the Russians for their first census. Although the machines were impressive, the heart of the system was the punched card. Jacquard had used it successfully to automate his loom, and even Babbage had planned to program his engine with cards. But Hollerith turned the small piece of cardboard into a key to wide-scale data processing. This brings us to the end of the 19th century. Let's take a look at the state of the art at the beginning of the 20th century and at a few of the developments that brought us to the age of the computer. After George Boole had published his method for solving problems in logic in 1854, a number of logic machines were built. The first of these Boolean logic machines to solve a problem faster than it could be done by hand was Jevons' logical piano. The elements for logical automata existed. Self-regulating machines using feedback, such as the steam engine with ball governor. Machines could be programmed by punched cards and paper tape. Alan Marquand, a Princeton professor, had developed a machine that solved very simple logic problems. But in his correspondence with the then philosopher Charles S. Peirce, he showed deep insight into what machines could actually be. In commenting on Marquand's machine, Peirce suggested that a system of batteries and switches could be hooked up to solve very difficult problems in formal logic. This would include most of the theorems of algebra and geometry. This is remarkably like the idea basic to the modern computer. All arithmetic operations have an electrical counterpart. Peirce could see these machines used to compile statistical information for science, aiding in the identification of fingerprints, and even in the realm of sociological studies. While businesses were being overburdened with manual methods of dealing with systematically collected information, Hollerith's tabulating system had been built. But even though the business machine industry got underway in earnest with the comptometer and Burroughs machines, analog devices to calculate tides were still being used in both England and America. And even though typewriters had been invented and were liberating women from the home and the factory, it would be several years before further improvements in this area would be seen. Under the pressure of business growth, some companies had been hiring men trained as rapid mental calculators. These men set the performance standards that early adding machines would have to surpass. But only after masses of government census data had been quickly and automatically processed by the Hollerith machines did large industries now begin applying the machines to their own data handling problems. Chief among these industries were the railroads, but also public utilities, and of course insurance companies. And with the advent of World War I, even larger amounts of information were needed on subjects ranging from ballistics to how many pairs of socks the Army needed to order. And the electric accounting machines were the answer. As the needs grew, the machines improved. The key punch, shown here, the verifier, and the sorter each received enhancements as they became necessary. Even the collator and the tabulator, shown here, could be improved upon. For all of this explosion, no radically new concepts evolved from the data processing industry from 1890 to the late 1930s. Nevertheless, some very significant technological discoveries were made within the communications and electronics industries, which ultimately had profound effects on the course of data processing. For example, in 1888, Oblin Smith made the basic suggestion for magnetic storage of data, and in 1895, Poulston invented the magnetic recorder. And then in 1919, Eccles and Jordan discovered that two triode valves could be connected to form a circuit possessing two stable states, the basis for the so-called flip-flop circuit, capable of storing binary information. Later, in the IBM 701 computer of the early 1950s, this storage of binary data was accomplished with vacuum tubes. In the mid-1930s, Bell Laboratories invented the automatic relay switching system for direct dialing of telephone calls. It was this invention that was to have the first major impact on changing the operational concept of data processing. In 1939, a group from Bell Labs, under the direction of George Steinitz, began work upon the first of three mathematical calculators. The first of these, called the complex computer, employing over 9,000 telephone relays, was completed in 1940. Used for multiplication and division of complex numbers, it could perform one addition or subtraction every 3/10 of a second. Programming instructions and routines were entered via paper tape. The system had a form of time sharing. 6 teletype units could be hooked to a computer to enter or print data. The system could handle multiprocessing by combining a number of computers to solve several problems concurrently. In 1937, as the complex computer was still being developed, Howard Aiken proposed a new kind of calculating machine. He wrote in his proposal, "There exist problems beyond our ability to solve, not because of theoretical difficulties, but because of insufficient means of mechanical computation." In 1939, 4 IBM engineers and Aiken began design and construction at IBM Endicott, New York, of this large-scale automatic digital calculator. The automatic sequence-controlled calculator, or Mark I as it is usually called, was designed to perform computations by following automatically a sequence of instructions prepared by a programmer. Instructions were fed into the machine on paper tape, cards, or by switches. The numbers upon which the instructions were to operate were stored in registers. The Mark I was an electromechanical machine. Its basic operations were performed by mechanical parts, which were controlled electrically by about 3,000 relays. Although already obsolete by the time it went into operation at Harvard in 1944, the Mark I operated for more than 15 years and produced valuable mathematical tables. Howard Aiken, who was familiar with the work of Babbage, once remarked, "If Babbage had lived 75 years later, I would have been out of a job." While the Mark I was solving U.S. Navy math problems, plans were underway for the machine that was to make the breakthrough from automatic processing to electronic operation. During World War II, the United States Army had tried to improve the differential analyzers used by Aberdeen to calculate ballistic tables. It still took 2 to 3 months before a table could be completed. Doctors John Malkley and Persper Eckert thought that a digital calculator could do the job. So in April 1943, through the Moore School of Engineering at Pennsylvania, they submitted a memo describing an electronic analyzer that would compute a trajectory and complete a table within 2 days. The Army bought the machine and had it constructed at an expenditure of some 200,000 man-hours. Truly an electronic machine, the ENIAC, an acronym for Electronic Numerical Integrator and Calculator, used vacuum tubes. It contained no moving parts except for input-output gear. It had 500,000 soldered joints, 18,000 vacuum tubes, 6,000 switches, and 500 terminals. Counting was performed by electronic pulses. The machine operated on the decimal system, and output was on punched cards. ENIAC did not originally contain internal storage. However, during construction, the idea was discussed and storage was added later. Although ENIAC best performed the job it had been designed to do, calculating ballistic tables, it was also used for many other types of scientific problems, such as weather prediction, atomic energy calculations, cosmic ray studies, thermal ignition, random number studies, and wind tunnel design. By 1945, 3 major lines of development, logical, statistical, and calculating machines, had come together to form the electronic computer. One more insight was needed to bring together the modern computer. In 1944, the Army asked the Moore School to build a more powerful computer than the ENIAC. A year later, John von Neumann responded with a complete logical design for a machine to be called the EDVAC, Electronic Discrete Variable Automatic Computer. In his paper was embedded the idea of a stored program. He suggested that instructions for the computer, previously entered on punched paper tape or by plug boards, could be stored in the computer's electronic memory as numbers and treated exactly the same way as numerical data. For the first time, logical choices of program sequences could be made inside the machine, and instructions could be modified by the computer as it went along and the program progressed. Building on all that had gone before, this fundamental concept led to the electronic stored program digital computer of the 1960s. In conclusion, I would like to return to the words of Charles Babbage. He once said, "Half a century may probably elapse before anyone will attempt so unpromising a task as that which I leave behind me. And, if unwarned by my example, any man shall undertake and shall succeed in really constructing an engine embodying in itself the whole of the executive department of mathematical analysis upon different principles or by simpler mathematical means, I have no fear of leaving my reputation in his charge, for he alone will be fully able to appreciate the nature of my efforts and the value of their results." Well, it took more than half a century, but today there is a flourishing industry that pays its homage to Charles Babbage.
Well now, that was quite a walk down memory lane for me, thinking about my time as a volunteer for the Computer Museum of America. Back then, I was a student at Coleman College, who provided major funding as well as some display space for the museum's holdings. I'm also reminded of my studies and the friends I made while attending Coleman College, which later became Coleman University. I actually graduated with a 4.0 GPA, summa cum laude, with a bachelor's degree in computer information science. Good times. I was really proud of that achievement. All in all, I think the reboot of this slideshow turned out pretty well. If you consider that by the time I received these materials back in 1997, the slides were already over 20 years old, and back then we didn't have access to great digitizing and scanning equipment, so the images were not of the greatest quality. For this reason, I have scoured the internet for better images and have used them in this iteration of the slideshow wherever possible. I've also kept the original audio track that I recorded back in 1997, but I had to filter out some of the background noise to make it usable. I think it turned out okay. Why don't you let me know what you think? Anyways, I guess that's it for this video. Remember, please click like if you happen to enjoy this video. If you haven't done so already, I'd really appreciate it if you would please click on the subscribe button. And if you would like to be notified when I publish future videos, just click on that bell-shaped notify button. Additionally, I'd love to hear from you, so be sure to leave me a comment and please share this video with anyone you think might enjoy it as well. Bye for now.